Welcome back. So we were talking about gradient descent algorithm, and we introduced it, and we were talking about its performance. And if you remember, using our main proposition, we sort of were able to show that the accumulated suboptimality when you run the gradient descent algorithm can be bounded by something like this, right? And we say that we desire this to grow gracefully with the total number of iterations, and this could happen if we have a control on how large the norm of these gradients are, okay? To make it formal, we're going to specifically focus on a class of functions that for them we can guarantee the norm of the gradient is uniformly bounded, let's say by some constant g, okay? And that class is basically the class of G-Lipschitz functions. So these you can imagine that they are continuous functions that we have some control on their degree of continuity. Okay, so let's first go over the definition, and then I'll try to build some intuition. All right, so here's our definition. A function in f is G-Lipschitz if and only if this inequality is satisfied for some constant g and for all vectors x and y. Okay, so what's the intuition here? We are essentially bounding the changes that could happen in the function value as a result of changing the input. Okay, so essentially we have, if you will, bounded sensitivity. We have a control on the degree of sensitivity. In other words, we have a control on the continuity of the function. Okay, the larger this constant g is, which we call it the Lipschitz constant, if we change the input slightly, we're going to see a larger change in the function value. And if g is small, in the extreme case, when g is equal to 0, if I change the input, there is not going to be any significant change in the output. Okay. For instance, let's consider the function fx equal to some constant. Let's call it 3. Okay. So the difference between fx and fy for any different x and y is 0. Okay. So in some sense, this is a function that is highly robust with respect to the changes in the input. Okay. Now let's get more intuition, and another way to think of this definition is that we have a bounded slope. Okay. So by rearranging, we can think of this as a slope, right? Why? So if you recall from your calculus courses, if I have a function here f, and this is the x-axis, okay? So a slope of the function can be defined as basically sort of the angle that is forming, right? So here, for instance, the slope is equal to 1, okay? But if I consider a function that is more sensitive with respect to the changes in the input, you expect to have, let's say, so let's say this is my function. So you expect to see a larger slope. Okay, so for instance, here the slope is equal to 2. So another way to think of Lipschitz is that it provides a bound on the slope. Okay, and the smaller it is, the smaller the slope. Therefore, the less sensitive the function is with respect to the changes in the input. Okay, and think of this as a slope is also useful because a gradient is nothing but basically a slope in higher dimension, right? So you should think of the norm of the gradient as a slope. So this is basically kind of a slope. Okay. So therefore, Lipschitzness, if a function is Lipschitz or G-Lipschitz, we are saying that the slope is bounded, or the gradient norm is bounded uniformly by this constant g. So therefore, you should be able to see that this is a definition that's going to be useful for us to leverage in our previous result and show that the accumulated suboptimality of the gradient descent algorithm grows gracefully with the total number of the iterations. Okay. So as I'm summarizing here, a function is if the function is differentiable, we can say that it is Lipschitz if there exists a uniform bond on the norm of the gradient. All right. So before going back to our discussion on gradient descent, let's go over some examples of functions to see whether they're Lipschitz or not. Okay. So first example is a square root function, and we want to see whether this function is Lipschitz or not. Essentially, has a bounded slope or not. When x belongs to this interval versus x belongs to the second case, the interval between 0.5 and 1. Okay, so let's see what do we expect. Okay, so if I draw the square root, it's something like this. So this is the function f of x equal to a square root of x. Okay, this is the x-axis. This is 0, and then let's say this is 1, etc. Okay, so as we can see here, when x is approaching 0, right, this tangent line becomes a vertical line. Essentially, the slope is approaching infinity. Okay, so here, slope is equal to infinity. So we expect that when x is near 0, the function is not Lipschitz because we cannot uniformly bound the norm of the gradient. And that is indeed true, right? So the easiest way to calculate the Lipschitz constant of any function is to calculate the gradient. In this case, it's a one-dimensional function, so we just have to find the derivative. What's the derivative of f? Just 1 over 2 square root of x. And here we can see that as x approaches 0, the gradient approaches infinity. Okay, so therefore, this case is not a Lipschitz function. So the square root is not a Lipschitz function when x belongs to this interval. Okay, because we can get arbitrarily close to 0 here. On the other hand, for the second case, you can easily see that it is Lipschitz. Why? Because I can uniformly bound the gradient for all x's that belong to this interval. Okay, so we can show that for all x belonging to the interval 0.5 and 1, the gradient is at most 1 over. So the gradient or the derivative in this case is a decreasing function of x. So it is at most 1 over 2 times a square root of 0.5. And this is some number which is bounded, right? So it's not infinity. So therefore, in this case, the function is actually Lipschitz. Okay. All right. So the second case, the absolute value function. So let's first draw to see how this function looks. Okay. So here, again, we can determine whether it's Lipschitz or not by looking at the slope. So here the slope is equal to 1. Here the slope is equal to -1. Okay. So for all cases, the slope is bounded. So here I want to point out that the function is not differentiable, but that's okay. Okay. So for almost all points in R, the slope is bounded. Therefore, the function is actually Lipschitz, right? And again, you can also show it mathematically, right? So what's the definition? The definition is that the function is Lipschitz if this condition is satisfied. So for the absolute value function, this is nothing but saying that this is less than 1 times itself. Okay. So therefore, this function is Lipschitz with the Lipschitz constant of 1. All right. Now let's move on to the next example. So the exponential function. So it grows very fast with x. Okay. So what's the derivative? Again, a simple approach to find the Lipschitz constant is typically to find the gradient. Okay. So the gradient here is the exponential function itself. And here you can see that if there is no restriction on x, this can go to infinity as x goes to infinity. So in this case, the function is not Lipschitz On the other hand, when I restrict X and say that, hey, it belongs to some closed interval or a closed compact set, if you will, the norm of the gradient or derivative in this case is actually bounded. In particular, this is an increasing function in X, so f prime is less than or equal to e to b. So therefore, this is my Lipschitz constant, and this is bounded. All right. Now I hope you're seeing a pattern that sometimes a function may not be Lipschitz globally, but if we consider the function locally, it may be Lipschitz, right? And in fact, that's typically the case, that for all practical regions of interest, we can assume that the functions are Lipschitz at the cost of having a very, very large Lipschitz constant, okay? And that could impact how loose the bonds that we are establishing are going to be for our training algorithms. All right, so let's also go over the last example. Again, so the x square function, it looks like something like this. What's the derivative? Is basically 2x, and it goes to infinity as x goes to infinity. So we cannot bound the derivative uniformly with some constant. So in this case, the function is not Lipschitz. On the other hand, it will be Lipschitz if we restrict the domain of the function to some closed compact set. In that case, f prime is basically less than or equal to 20, basically, right? So therefore, when I restrict it, the function becomes Lipschitz. All right, so hopefully these examples give you an idea of what kind of functions are Lipschitz, what kind of functions are not. And the main idea is that functions that have a bounded gradient norm, essentially the slope is bounded. They are Lipschitz. We have a quantified way of talking about how sensitive the function is with respect to changes to its input. And many times we can, if we put our focus to a specific interval, which is closed and compact, we can assume that the function is actually Lipschitz, despite some functions not satisfying the Lipschitz condition globally. All right. With that, let's see and talk about the implication for the gradient descent algorithm. Okay. So now, in addition to convexity, we are imposing that our function is G Lipschitz. And again, the main idea is that we want to have a control on how large the gradient that we are observing as we run the gradient descent algorithm become. Okay. Now, let's also define this shorthand notation D, which essentially captures how close to the optimal solution, or one of the optimal solutions I am at initialization. Okay, so this is a measure of the error at initialization, essentially. So from our proposition, if you remember, we established this bond on the accumulated suboptimality of the gradient descent algorithm. Now, by Lipschitzness, the following theorem is going to become almost trivial. So if the function is G Lipschitz and convex, gradient descent, which if you recall followed this specific update, where we update our parameter by going to the opposite direction of the gradient while incorporating a specific learning rate eta, is going to satisfy the following suboptimality gap, as long as I set the step size or learning rate to be something like this. Okay. So what's the bound? So basically what I've done, I just plugged in this eta into this inequality and divided by t, okay? And this gives me the following bound. And the way to interpret it is to say that now the average suboptimality is bounded by dg square root of t, okay? So let's see what the bound says. It says that on average, you're going to find the optimal solution as you increase the total number of iterations, capital T. Okay, so as I run my algorithm more and more, I'm going to find the optimal solution. I'm going to get closer and closer to the optimal solution. I'm going to reduce the suboptimality of my solutions. Okay. It also says that if you are further away from the initialization, you're going to have a larger bond because D appears in the numerator. And similarly, if you're optimizing a function that is more sensitive, you may need to, you're going to potentially converge slower. Okay. So if the function has a, again, better condition, lower sensitivity, if you will, we should be able to optimize it more easily. All right. So you may ask how we can calculate this step size or why we are calculating this step size. Essentially, what will happen is that we're going to have, let's say, error less than or equal to some bond, and this bond is a function of eta. So what we have done, basically, we have minimized this bond as a function of eta and find the best step size, if you will. We have found the best constant step size. Okay? And this is a very simple optimization problem. So it turns out that the bond as a function of eta is sort of equivalent to minimizing a quadratic function. So by just taking the gradient of that, you should be able to find its step size. All right. So let's talk about some remarks. Essentially, I first want to talk about how to output the solution, because the last result only tells us what's the average suboptimality gap. All right. And in particular, I want to talk about three approaches. The first approach is typically what we do in practice, right? So we run the algorithm for a certain number of iterations, let's say 100 iterations, 1,000 iterations, etc. And we set our solution to be what is the last iterate. What's the last point we find after running the gradient descent algorithm? Okay, and the idea here is that in practice this tend to enjoy better performance, meaning it tends to enjoy lower suboptimality. Okay. One, if you will, drawback of the analysis we presented in this course for gradient descent is that we cannot guarantee whether the last solution is going to be enjoy the best performance or not. So for that, we need a different analysis, a more complicated one, if you will, and that is beyond the scope of this course. But the main idea is that the role of the step size becomes a lot more crucial, and we have to actually change the step size when we go from one iteration to the next. Okay, and this is something that we're going to talk about later in the course when we discuss the importance of learning rate tuning when optimizing deep learning models. All right, but there are two other solutions for which the analysis we presented actually lead to provable guarantees. The first one is, instead of outputting the last solution, what you do, you take the average of all the iterates you've encountered when running gradient descent. Okay, so this is basically the solution we're going to output. Now, why is this a good idea? Remember, we assume that our function is convex, so we can leverage the convexity definition to show that this solution enjoys a provable theoretical guarantee. So this is the bound we found on the average suboptimality gap. Okay, and it turns out, again, by using convexity here, this average suboptimality is going to be larger than basically the suboptimality of the average solution. Okay, and here I'm just using the first definition of the convexity, convex functions, right? If you recall, the definition was, for instance, f of lambda x plus 1 minus lambda y is less than or equal to lambda f of x plus 1 minus lambda f of y. Okay. Essentially, we are saying that the value of the function at midpoint here is lower than the average of the function values. All right. So therefore, by convexity, taking the average of all iterates is going to be a solution that enjoys a provable bound on its suboptimality. But I want to point out here that taking the average only makes sense if your function is convex. Okay, so in practice, especially when it comes to optimizing deep learning models, this is not going to be something meaningful. Okay, and the idea is that if you have a non-convex function, let me show it here. You may have two solutions that are globally optimal, but once you take the average, you may find a solution that is actually locally a maximal, a local maximum of the function. Okay, so taking the average only makes sense if the function is non-convex, where we're not going to encounter these cases that arise due to non-convexity. All right, and the last way of outputting a solution is, I would say, an approach that is preferable when you are stating theoretical guarantees, especially for non-convex functions. Okay, so what we do here, we basically sample one of the iterates that we have encountered when we were running the gradient descent algorithm uniformly at random. So what that means is that, let's say I run my gradient descent algorithm for 100 iterations. To output the solution, I'm going to pick the first one with probability 1 over 100, or I'm going to pick the second one with probability 1 over 100, etc. Okay. Now, on expectation, this randomized solution is going to satisfy the same bound that we found before. Okay, and the reason for that is that we are outputting the solution uniformly at random. So this expectation is exactly equal to the average suboptimality. Okay. And one idea behind this is that as you increase t, as you run your algorithms for more and more iterations, the later iterates are going to be very, very similar. Therefore, it's going to be more likely that we select something that resembles the later iterates. So therefore, we're going to sort of emulate the performance of the last iterate, which we expect to be better. All right. So let's talk a little bit more about the bound that we found. So again, the bound was that average suboptimality is less than dg over square root of t. Now, I want to talk about a few things. First of all, it is sometimes useful to hide the constants, in this case, d and g. And you just focus on what's the rate at which the error goes to 0 with respect to the number of iterations. Okay, and in this case, we use what we call the O notation, right? So O notation just hides the constant and mainly focuses on the total number of iterations, if you will. So in this case, the rate at which the error goes to 0 is sort of 1 over square root of t. And we call this a sublinear rate, as we discussed in our optimization, basics of optimization lecture. Another thing that I want to point out is the role or the regulating role that the layering rate plays. Okay, so the layering rate is proportional to d, but inversely proportional to g. So to interpret this, we can think of eta doing the following. If we are further away at initialization from the optimal point, eta has to be larger to make sure we converge faster. That's why d appears in the numerator, right? So the further away we are at initialization, the larger the step size has to be. On the other hand, the sharper the function is, the more sensitive the function is, we have to be careful with the steps we are taking. So we have to make sure that the steps we are taking are small, such that we converge. Okay, so that's why g appears in the denominator for the best constant step size. One drawback of this step size is that it depends on d, which is the sort of the error at initialization, and g. So these two constants are not necessarily known in practice. For instance, D, to know D, we have to sort of have an idea where the optimal solution is, or where one of the optimal solution is located. Okay, so this is a quantity that we don't know, therefore we don't know D, right? That's why there has been a lot of development in the past few years to devise algorithms that are sort of adaptive, meaning that they can estimate these unknown quantities that are essential for the convergence of these algorithms on the fly as you are running the algorithm. And this is something we're going to talk about later on in the course. All right. So one other remark is that there is no explicit dependence on the dimension. So we assume that W is a d-dimensional vector. So if you have a neural network with 100 million parameters, D is basically 100 million. Now, here in the bond, a small d doesn't show up at all. And this is very desirable. Is a very desirable property of the gradient descent algorithm. That's why we call these kind of results dimension-free results, to mean that there is no explicit dependence on the dimension. And indeed, there are algorithms in the optimization literature that are not dimension-free, such as the ellipsoid method. This is one reason that we don't see these classical optimization algorithms to be applied in machine learning and deep learning optimization problem, given how large a scale the problem that we are facing are. And however, I want to point out that D typically finds its way implicitly in the bond. And in this case, it finds its way through G and D. Okay? And the easy way to see this is, again, let's talk about the initial error, the difference between W and W star. So these are d-dimensional vector. So if I assume that each coordinate is some constant, let's call it a small c, I should expect that, for instance, d square is just somewhere I from 1 to d of the differences between the coordinates. So W, the ith coordinate of Wi, W1 minus the ith coordinate of W star square. And if each coordinate is some constant, this is something like d c square. Therefore, D is basically proportional to a square root of D. So although there is no explicit dependence on the dimension, there could be implicit dependence on the dimension through the constants, such as the initial error as well as the Lipschitz constant. All right. So it is also sometimes useful to think about iteration complexity or describe the bond that we find through the lens of iteration complexity. So this basically means that what should be the total number of iterations to find an epsilon accurate solution. Okay. So essentially what you do, you set this side to be equal to epsilon and do some rearranging to find the minimum number of iterations that you need to run your gradient descent algorithm such that the average suboptimality is at most epsilon. Okay, so we are epsilon close to a solution. And if you do so, this is what you're going to find. And this is the way to use the O notation here to hide the constant and say that the iteration complexity is basically 1 over epsilon square. Okay. All right. And the last remark is, so what we have done, we have provided an upper bound on the error. Okay. And you could ask whether this is a good upper bound or a bad upper bound. Is the bound tight or not? So this is a question that is relevant to driving lower bounds, right? So what's the best that any algorithm can do when optimizing a function if that algorithm has only access to, let's say, the gradient information? Gradient descent is one algorithm. Maybe I can come up with a better algorithm. Okay. It turns out for this class of function, convex and Lipschitz, we can't do better in the worst case. However, I want to point out that the practice is typically nicer. So we could, in practice, have algorithms that converge faster than the gradient descent algorithm. And that's basically what motivates us to design algorithms, training algorithms, to optimize deep learning problems more efficiently. So in the next lecture, we're going to talk about a variation of the gradient descent, which is more applicable to larger scale problem, and that's a stochastic gradient descent. I'll see you next time.